For centuries people have placed the highest value on diamonds that are not only large but flawless. Scientists, however, have discovered exciting new applications for diamonds that are not only incredibly small but have a unique defect. In a recent paper in Applied Physics Letters, researchers at the University of Rochester describe a new way to measure temperature with these defects, called nitrogen vacancy centers, using the light they emit. The technique, adapted for single nanodiamonds by Andrea Pickel, assistant professor of mechanical engineering, and Dinesh Bommidi, a PhD student in her lab, allowed them to precisely measure, for the first time, the duration of these light emissions, or excited state lifetimes, at a broad range. The discovery earned the paper recognition as an American Institute of Physics SciLight, a showcase of what AIP considers the most interesting research across the physical sciences. The approach is also safe for imaging sensitive nanoscale materials or biological tissues and could have applications in quantum information processing. It turns out these lifetimes are quite fast, only about 25 to 30 nanoseconds at room temperature, and even faster at higher temperatures. New technique offers multiple advantages over standard approach. Nitrogen vacancy centers are often created by bombarding commercial diamonds with ions, then emit. In a nitrogen vacancy center, one of the carbon atoms is replaced with a nitrogen atom, and the adjoining nitrogen atom is missing. It turns out, these nitrogen vacancy centers are fluorescent, so if you send light in, from a laser, for example, you can also get light out of them, Pickel says. To date, most research groups have used a technique called optically detected magnetic resonance, ODMR, to measure temperature using nitrogen vacancy centers. However, the method has several drawbacks, Pickel says. OMDR requires placing a microwave antenna near the sample to do the measurements. That can be a complicated setup. The antenna can also cause heating that could harm sensitive materials or biological samples. Moreover, the microwave signal can be lost altogether at higher temperatures. The researchers then excite the nitrogen vacancy centers with green laser pulses. This sends electrons into a higher energy state. When the laser shuts off and the electrons return to a normal state, photons are emitted. The duration of this emission is a precise indicator of temperature. Because the nanodiamonds are the same temperature as the material they are placed on, the readings are accurate for the material as well, Pickel says. We are excited about this because it is all optical. We don't need to have a microwave antenna, Pickel says. And even when we increase the temperature, we retain access to our measurement signal, so we can make temperature measurements at pretty fast time scales. That's important at the nanoscale, because when you have really small samples, they can change temperatures really fast. Materials provided by University of Rochester. Original written by Bob Marcotte. Note: content may be edited for style and length. Dinesh K. Bommidi, Andrea D. Pickel. Temperature-dependent excited state lifetimes of nitrogen vacancy centers in individual nanodiamonds. Retrieved January 26, 2022 from ift.tt/35-TYRB2 University of Rochester. Using nanodiamonds as sensors just got easier. Science Daily. ift.tt/35-TYRB2. Access January 26, 2022. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.